is Catherine?
We're missing, looks like about 4. So I think we can get started.
Great. Okay. All right, as promised, we have an ionosphere expert with us today, Shasha Zhao at the University of Michigan, who is going to answer all of the questions that I wasn't able to answer yesterday.
I'll try my best.
Okay, great.
Thank you, Nick, for the introduction.
Yeah.
So, hi everyone. Hi. Hello here from University of Michigan in Ann Arbor. My research interest is about the magnetosphere, ionosphere, and thermosphere coupling in the geospace system. And so today I'm going to talk about my favorite topics. Yeah. So hopefully you will enjoy it as well. So you probably noticed that I added one more terms here to the title, the thermosphere, in addition to ionosphere, because those two needs to be considered together. They share the same space, but they are governed by very different physics. So makes the ionosphere and thermosphere regime a very interesting area for us to study. I borrowed this plot here from the NASA Goddard Scientific Visualization Lab. They produce those fantastic plots and movies for us to use. So what is plotted here is the color contours are the ionosphere F-region density. So you can see some large scale, really large high density regions as red, and then lower densities close to the polar regions. You can also see there are some really tiny vectors. Those are actually the thermospheric wind based on an empirical model. And so this plot nicely shows the ionosphere and the thermosphere interact and coexist in the same space. So next I'm going to just play this as a movie, so just to give you a visual impression of what ionosphere and thermosphere should look like. So we are looking, you can see the continents underneath, right? So we are looking at the American sectors. As the day goes on, you can see now we are in the dawn sector, and gradually we are migrating to the noon sector. That's where you see those red bands. And today we will get a chance to talk about the formation and the dynamics of those bands here as well. And this is a different view, and you can see here is the magnetic field near the equator, and you can see those vectors of the thermospheric winds. They are very dynamic. Okay, so we'll learn all of those today. So there are some basic definitions about thermosphere and ionosphere. As I mentioned, they exist in the same space, right? But their definitions are actually based on different physical quantities. For example, for the thermosphere, it is the uppermost part of the atmosphere. And we know the different layers of the atmosphere are determined by the temperature gradient. Starting from the surface of the Earth, we're in the troposphere, where the temperature is actually gradually decreasing while you move to higher altitudes. And then we move to the stratosphere, the mesosphere, and eventually somewhere around 85 kilometers, 90 kilometers, we start to get into the thermosphere. And you can see there is a very rapid temperature increase in the thermosphere until about 200 kilometers-ish, where the temperature becomes isothermal. So this region determined by the temperature here is what we call the thermosphere. And the thermosphere refers to the neutrals. When we talk about thermospheric wind, we are talking about the neutrals that are moving, and those are the neutral winds. The ionosphere coexists with the thermosphere. The lowermost region of the ionosphere is usually the E region, and occasionally we can have a D region that's extending further lower to almost 70 kilometers. And above that we have the F regions. So the ionosphere, the definition is based on the plasma number density. And the different layers you can see are based on the shape of the profile. There is one bump at a lower altitude. This is the E region, and there is another bump, a much bigger one. That's the F region. So you can see, although the thermosphere and the ionosphere exist in the same space, but one refers to the neutrals and another one refers to the plasma. The ionosphere is based on the ionization of the thermosphere neutral particles. So when we talk about the ionosphere, we have to talk about thermosphere at the same time to understand their dynamics. Okay, so here this is a chart showing you the typical, like condition on the noon sector and then during solar maximum. The light blue curve shows the electron density profile, and then the yellow one shows the neutral density profile. So the purpose of showing this one is to give you an impression of the relative abundance of the plasma and the neutrals in this region. So you can see even during the, or at the 300 or 400 where the plasma reaches its peak, this density is still orders of magnitude smaller than the neutral particles. So this important information tells us the ionosphere is a very weakly ionized plasma. The ionization rate is as low as like 0.1%. So this also tells you that the ionosphere dynamics can be strongly controlled by the neutrals. Because if you think about, you are one of those ionosphere plasmas and there are 1,000 of those neutral particles surrounding you. So it would be very hard for you to move around without collide with those neutral particles in the surrounding region. So understanding this density ratio here is very important for a lot of the dynamics that we are going to talk about in the later part of the lecture. Okay, so this slide we will talk about the thermosphere major compositions. We know that the atmosphere just outside our house, most of the neutrals are molecular N2 or O2, right? But when you move to the thermosphere altitude, you start to see those atomic neutral particles, such as atomic oxygen or hydrogen and helium. And so one of the important things to understand their generation is to understand a process called a photodissociation. I will talk about that in the next slide. Here, another thing I want to emphasize is that below about 100 kilometers, the 100 kilometers is usually what we call the turbopause. Below that altitude, all of those different constituents within the neutral atmosphere are very well mixed with each other. So when they move to higher altitudes, their density decreases almost following the same rule. So they share the same scale height. I know that the concept of scale height has been introduced in earlier lectures. So today I'm not going to talk about the details of that. Above 100 kilometers, those neutral particles start to deviate away from each other, and then their density are now controlled by their own scale height. So if you look at the equation of the scale height, you have the mass here in the bottom, right? So this tells you that if you have a lighter neutral particles, that means your scale height will be larger, considering they are sharing the same temperature. So what that means is this light particles, their densities will decrease much slower than the heavier particles. This is very well represented in those empirical models. If you look at here, for example, the magenta color is O2, and O2 is the heaviest here, right? So you can see the O2 density decreases very rapidly as we move to higher altitudes. On the other hand, let's look at oxygen, because oxygen, the atomic one, is very important. The atomic oxygen starts to disappear, starts to appear around this 90 or 100 kilometers. And then gradually their contribution increases. Somewhere around 170 kilometers, the atomic oxygen actually becomes the most abundant neutral species here in the thermosphere and ionosphere regime. So understanding the formation and the dynamics of the atomic oxygen is very important for us to understand the IT system science. Okay. I think Dana has shown this picture before, or a similar one in an earlier lecture. This one shows the solar energy deposition altitude. What is important here is you can see there are also the different neutral compositions shown, right? Like O2 is here, N2 and O are also shown here. And this is as a function of the different wavelengths and altitude. So the location of this, or I should say the span of those arrows, indicate that those solar irradiance or the radiation or the photons can be absorbed by the neutral atmosphere. When you see the neutral particles are marked here, that means those solar radiations are absorbed for dissociation of those molecular neutrals. And the dissociation of those molecular neutrals can turn them into the atomic gases. So like the O2 will be turned into O, as you will see in the next slide. During this photodissociation process, actually let's go there. So here this one shows the chemical reactions of the photodissociation. So if we have, actually this should also be mu here, like the photon frequency. So when we have the solar radiation that hit one of those molecular species, and those molecular species will become two atomic ones. And during this process, they will absorb some part of this energy from that photon, right? So on the right, I marked some of the typical energies that they need to absorb in order to dissociate the molecular species. So you can see here some of the major molecular species in our atmosphere, O2, N2, H2O, and they can be photodissociated into the important atomic species O, N, and then H here. So those ones are the most important photodissociation equations that's happening in the thermosphere and produce those important atomic species that we saw in the thermosphere, but they do not exist at a lower altitude. If I go back to the slide, besides those neutral particles you see marked here, you can also see the ions. So the location of where those ions are marked indicate the longest wavelengths of the photons that can ionize those particles. So the easiest one to be ionized here you can see is NO, right? And it will become NO plus. It takes about 140 nanometer solar radiation. The hardest one would be the N2 plus, which needs the solar radiation needs to be like close to 70 or 80 nanometers. So remember that when you look at this plot, the energies increases while you move to the left, okay? And that's where you see the wavelengths of those photons decreases. So the photodissociation and those ionizations will absorb the solar radiation energy and then convert them into the particles, thermal energy, and some of the leftovers during that chemical reactions will go into their kinetic energies. Okay, I can skip that one. So here I want to talk about some of the seasonal variations and the latitudinal variations that you would expect to see in the thermosphere. As I mentioned, the solar radiation is very important to photodissociate the thermosphere molecules and also to heat those neutrals, right? So that means on the day side, where you directly face the sun, those regions will be the ones heated the most, right? So then you should expect to see a very clear diurnal variation of the thermosphere density and their temperature. So if we look at the middle one, this is the March equinox. It's easier to start with the equinox. So during the equinox, the sun is sending the same amount of energy in both hemispheres. We expect to see the minimum hemispherical symmetry. So as you can see here, it's pretty symmetric in terms of the northern and the southern hemisphere. The largest thermosphere density and the temperature, which is now shown here, will be on the day side. It's actually not right at the noon, but slightly off, around like 14 or 15 local time, because it still continuously accumulates those energies while the Earth is rotating westward. So this is why the peak usually occurs 2 to 3 hours east of the noon sector. If you look at the December or the June solstices, there is very clear hemispherical symmetry, right? The peak now should shift to the hemisphere where the sun directly shines upon. So during the December solstice, you see this peak now shifted to the southern hemisphere, and similarly, in the June solstice, this peak should occur in the northern hemisphere, right? So this is like the zeroth level hemispheric symmetries controlled by the solar EUV and then the FUV radiations. Those are very important for us to understand the thermosphere, and later you will see the ionosphere symmetries. Okay, so we looked at that seasonal variations of the thermosphere density. Here I'm trying to show you the solar cycle variability of the thermosphere. There are two curves shown. The yellow one indicates the solar minimum, and then the red one is the solar maximum. This curve here, this area, is the thermosphere temperature, and this dashed line here indicate the thermosphere density. Okay, those two are directly correlated and controlled by that scale height parameters I just showed you. So during the solar minimum, the thermosphere temperature can be as cold as like 800 Kelvin. During solar maximum, this temperature can shoot all the way into like 1300 or even 1400 Kelvin. So there is a really large solar cycle variation of the thermosphere temperature. When the neutral gas is hotter, then they will tend to expand. So the thermosphere density is very sensitively controlled by this temperature. During the solar minimum, the density is the lowest, right? As you can see from here, because the temperature increases during the maximum, the solar maximum, so the density would also increase during solar maximum years. I saw there is a question in the chat. So one of the question is, are those variations the same in 100 and 200 kilometer range of the thermosphere? Are the student allowed to talk here? Because I just want to clarify the question of...
No, absolutely not. We don't allow the students to say a word. Luke, you wanna explain your question a little bit?
Yeah, like in the previous slide that you showed, those were the variations at 400 kilometer altitude in the graph. So are those variations same in lower thermosphere, like 100 to 200 kilometer range?
Yes, the variations can also be seen at lower altitude. That plot itself is about 400 kilometers, but if you plot from either empirical models or numerical simulations, you will see that also exists down to like 100, 200 kilometers. You can also see it actually from here. I can use this solar cycle variability plot to show you. If you look at the temperature here, right, and you can see that between this 100 and 200 kilometers, there is actually a very clear variation of the solar cycle. And similarly, there is one during the different seasons. But the variation, the seasonal variation will be much smaller than the solar cycle variation.
Thank you.
Okay, let's move on here. Now, finally, we start to talk about the ionosphere, right? So the ionosphere is the ionized portion, of the same altitude as I just mentioned, and there are different layers based on the density profiles. What makes the ionosphere very interesting is that the different layers, their formation and their dynamics are actually controlled by pretty different process. So here, if you look at the lower altitude, this is the E region. The E region and also the D region, their dynamics are highly controlled by the chemical processes. The E region can be considered as in chemical equilibrium. So what that means is the production and the loss of those plasmas in this region are all controlled by their chemical reactions. But when you move to higher altitudes, you start to drift away from the dense neutrals. It's still dense, as I just mentioned, because it's a weakly ionized regime, right? But the neutral density actually decreases very fast. So that means the collisions between the plasmas and the neutrals decrease very rapidly when we move to higher altitudes. So this will give those plasma in the F region a much longer lifetime. And so when they have sufficient time to move around, the transport process now becomes more important. And so when we consider the F region plasma dynamics, we have to combine the chemistries with the transport. So this marks the major difference between those different layers here. When you move to even higher altitudes, where the even lighter plasma becomes the dominant one, like the protons and the helium, we start to migrating away from what we call the ionosphere to plasmasphere, or in the earlier days called protonsphere. Based on the name, you can see the proton will be the dominant species, right? So in the mid-latitude, if you continue further, following the magnetic field line from the this topside ionosphere and all the way into the equatorial magnetosphere, that you will reach the plasmasphere. So the plasmasphere is the topmost regime of the ionosphere in the mid-latitude region. Okay. So on this slide, I want to introduce some of the important concepts. I saw that many of you, when you do your ionosphere lab, you already started to use those concepts. So for the F2 region, F2 layer is the most, I have to say, one of the most important layer of the ionosphere, because the peak density happens here, right? And so we created those acronyms to help us to make the things easier. For example, the NMF2 is used to refer to the peak density of the F2 layer. So that is this peak density right over here. Now the HMF2 is the peak height of the F2 layer. So that refers to the height whenever this F2 layer density reaches the peak. So those two parameters are often used to describe the F2 layer. Now, in the last 20 years, people started to use what we call the total electron content measurement. this becomes perhaps one of the most often utilized parameters for ionosphere research now. The total electron content refers to the sum of all of those electrons, or I can say plasma because of the charge neutrality, all of those electrons within the column between the receiver and then your GNSS satellite. So for example, in the US, we use GPS a lot. So the total electron content can be between the ground receiver and all the way to above the 20,000 kilometers where the GPS satellite is. So if you add all of those electron content together, that gives you the total electron content. Okay. You will see that the total electron content is a very important parameter to use. In some of the later slides, I will refer back to this concept as well.
Shasha, is this a good time to handle a couple of the questions from last night? There's a couple of questions on NMF2 and HMF2.
Let's wait for a little bit later because I need to introduce some of the chemistries before we look at that. Yeah. Mm-hmm. Okay. On this slide, I just want to show you, the ionosphere is a very useful layer for our daily life. A lot of the electromagnetic waves we send out for communication, those long distance communication, bended back by the ionosphere, and then we will be able to reach the locations where we wanted to reach, right? So for example, you can see here, if you have a transmitter here, the electromagnetic wave will be bended back and then received by the receiver. So the ionosphere, or people who operate those instruments, they need to consider the density of the ionosphere in order to choose the most appropriate frequencies to use for their communication. If you choose some frequencies that is too high, then that electromagnetic wave will penetrate all the way through the ionosphere and will never come back, right? And sometimes if you choose wrong frequencies, and they may be reaching a location which is too close and not your target, right? So in order to understand the frequencies that you want to use, and then you need to know the ionosphere density. People often create people created this one of those parameters called critical frequency. The critical frequency tells you the maximum frequency that you can use in order to bend your signals backward. Okay, so that means if you know your NMF2, that is the peak density in your F2 region, right? You can use this very simple and handy equation to get the peak frequency that you can use. If you plug in your density in number per cubic centimeter, you will get your frequency in megahertz. Most often, the ionosomes or those instruments that we use, HF frequency instrument we use, operate somewhere between like 3 to 30 megahertz. And based on that, you can see our ionosphere density can have a very large variation. And 3 to 30 megahertz range can help us cover most of those density variations. So when you adjust the frequency of your ionosound, and you will be able to successfully communicate. Okay, so here I just want to show you one of those ionosound measurements of the F region and the E region. So you can clearly see there are some long-term trends, right? This is the bottom here is a year, and this covers more than one solar cycle. So the solar minimum and solar max are marked here. You can see there is a very clear solar cycle variation of this peak F region critical frequency, right? So remember that handy equation I showed here. This tells us the higher the frequency, the larger the density. Right? Just keep this in mind. The higher the frequency, the larger the density. So when you look at one of those ionosound curves, you will see that during solar maximum, you are using a larger frequency, so that means the solar maximum, you get a larger F2 peak density, right? You get a larger NMF2. So by just reading those charts, this will give you information about the ionosphere peak density ranges that's changing during the solar cycle. So this is a long-term variation. And now if you look at a shorter term, between each one of those dips, you can consider this is like 1 year, right? So you can see there is a very clear, seasonal variation here as well. And actually within the same year, you will see there are 2 peaks and a dip here. So there is a interannual variation. So the ionogram, the long-term trend, provides us a lot of information about how the F region changes for different seasons, for different solar cycles. This is a very useful instrument for ionosphere physicists. Now here you can also see a curve for the E region, right? And the E region frequency is much lower than the F region. So what does it mean? Spend 15 seconds, think about that. Remember the handy equation. The higher the frequency, the higher the density. So here we see the E region throughout the solar cycle have much lower frequency than the F region. So what does that mean? So that means the E region density should be much lower than the F region density in this particular location, right? You can also identify the yearly variability and also very weakly the solar cycle variation here. Let's see. Okay. Now let's dig more about the ionosphere composition. The ionosphere are the ionized part of the thermosphere. So we have already learned about the thermosphere composition. Now we can understand the ionosphere composition. We can start from the F region. As I mentioned, in the F region, the thermosphere, the most important composition is the atomic oxygen. So the photoionization, that means you remove one of the electrons from the neutral oxygen, you will get O+, right? So the O+ is the most important plasma in the F region. Now let's look at the equation here. So here, the major source in the F region is the photoionization of the major thermosphere component here. That is the atomic oxygen. So now once you ionize it, you get your O+, right? The oxygen ions here. For the other layers, let's look at the E region first. So in the E region, the most abundant thermosphere component is the molecular N2, right? So that means the ionization of the N2 should be the major source for the plasma there. This is a major ionization source, but one thing you might be surprised to see here is that the N2 density in the E region is actually much lower than O2+ and NO+ here. So this is an interesting surprise, right? For the F region, we ionized the atomic oxygen, we get O+, and O+ is now the most abundant plasma here. No surprise. But in the E region, the N2 is the most important neutral particles. But surprisingly, the N2+ is not. Okay, so why is that? We need to look at the major loss process here. The N2+, once generated by the photoionization, will very quickly charge exchange with the atomic oxygen in the ambient region, and that will give you NO+ and another neutral N. NO+ will recombine with the ambient electrons very rapidly. So that's why in the E region, the N2 plus is actually not a major ion. The major ion is actually NO plus. The other important chemical reaction here is the ionization of the N2. Remember, N2 and O2 are the most important ones in the E region, right? And so the O2 is the next important source for the plasma there. And similarly, once you have the O2 plus created, the O2 plus can also recombine with the ambient electrons and generate two atomic oxygen. But because the N2 plus, because the N2 is much more, the number density is much larger than the O2, so that's why we get a lot of NO plus here as well. Although there are not many NO neutral in this region. So this might be confusing at the first sight, but if you take a look at this lecture slide after this, you will get a better idea. The recombination process here, we call them dissociative recombination. This is a very fast, those three equations, those are very fast chemical reactions. Comparing with the first step, the charge exchange, these three reactions happens 5 orders of magnitude faster than the first one. So this is why we still see this NO plus becomes an important plasma species in the ionosphere. So be very careful when you look at the ionosphere compositions. So the surprising thing is in the E region, the N2 plus is not a major ion, but the N2 plus and the NO plus are the most important ions here. Okay. So another thing that I want to mention is, actually I need to look at here. So you can see the recombination process here involves the ambient neutrals, right? So like for example here in the F region ones as well, where the O plus that was generated by the photoionization needs to first charge exchange with the ambient N2 and generate NO plus. And then the next step is the NO plus recombine with the plasmas in the surrounding region. So this means if we move the ionosphere away or towards the neutral layers, the ionosphere loss process will become either slower if we are moving away from it, or faster if we move the ionosphere towards the neutral. So this relative motion of the ionosphere and the thermosphere is very important for us to understand the ionosphere dynamics. Okay, so let's see. Now is probably a good time to bring up the lab questions that the students have.
Yeah, so a couple, one of them, let's see, just trying to, oops, shoot, that's not what I wanted to do. Here, I'm just going to do this. Save. Copy link. I'm going to put the questions I mined just in chat so you can read them. But maybe you can't get out of that. So why don't you, so let me find them again. And done. So, all right. So one group looked at the variations of between solar min and solar max. Why are the maximum values of NMF2 and TEC observed at 8 UT during noon?
Is there a chart that associated with this question, so it would be easier for me to look at them?
I believe there is. I think. Do you want me? You want me to share that? So I think whoever asked this question, is this the right graph?
Oh, yes, yes, it is.
Great. So you can see that you've got TEC on the left-hand side in black, and then NMF2 is in blue, and it's covered up, but the HMF2 is in red. And we're looking at a so there's height variations here, but it doesn't matter because these are height independent. So we're looking at a mid-latitude and around the world. So, and this is at a fixed UT.
Yeah, this is a very interesting chart because the TEC values here looks way too small.
Oh, I think it's log scale. But I could be, I'm not sure.
Okay, yeah.
I gotta go.
Yeah, if this is linear, this looks way too small. And then let's see, we have HMF2 and then NMF2 here. Yeah, this looks similar to one of the earlier questions that I saw on Slack. And so I indeed went to CCMC and made a couple of additional plots. So I can show those two plots, and then it will help us to understand those. Yeah, let's see. Okay, so I think this is a question submitted by Group 9 last night. They were looking at the northern hemisphere, 55 degrees, and then the plot you showed earlier is at 45, right? But at the same location. I'm sorry, the same UT. Yeah. So I think I can answer those two questions at the same time. Yeah. Also, this one, the TEC shows here is very small. What I did is I went to the CCMC, the CTP, and find this exactly the same time. I made a two-dimensional TEC plot. You can see the units, the scale here. So here you can see there is a very clear, like equatorial region with high density, right? And this is because, during the March equinox time, we have the solar radiation, the production peaked in this region. And I also looked at the run log to see what drivers were used for this run. It seems it's a constant F10.7 and a constant IMF. Yeah, so there is no temporal variation basically in this simulation. So here you can see this is the equatorial region. We will talk about the bifurcation later. But I think one of the questions submitted by Group 2 is why there are fingers. So one of the things I want to clarify with Group 2 is when you say fingers, are you talking about those two bifurcations? Do we have anyone from Group 2 that can clarify the question?
Yes, so it's we understand that there is this magnetic equator which is
Yes.
not plane, it's curved. So we understand that curvature, but that bifurcation, and they again this has, I mean, we have observed it throughout the time. So this just moves along the surface.
Yeah, yeah. So those two bands are the remnant of the equatorial ionization anomaly. So in this particular case, this here is where the terminator is, and the noon and afternoon sector is here. So behind the terminator, you see the solar radiation will shut down, right? And so the photoionization process that I just mentioned in the E region and F region, those will go away because we have no source for ionization. And then what's left to control the density there are the loss process. So in the E region, the loss process happens very fast, in seconds. So that is why after the terminator, you start to see the density decrease. They disappear almost immediately, the E region. but the F-region plasma have a longer lifetime because they are further away from the neutrals, so they can live for a few more hours there. So this is why you start to see those F-region plasmas can still exist there. This is one of the reasons. And another reason, the possible reason, I say possible is because I'm not familiar with CTPE model, and so I don't know whether they have the equatorial plasma dynamo that was included in the model. So in the real ionosphere, there is also what we call an F-region dynamo process that's happening beyond the terminator. And the dynamo process here will give you a enhanced, what we call the equatorial plasma fountain effect. They tend to move the equatorial plasma into the off-equator region. So those two bands could also be produced by that dynamo effect. So really depending on what the drivers are for this model, there could be different contributions to the formation of this structure. Okay, now let's go back to this one here. This one looked at the TEC region at 55 degrees, right? So if you draw a line here around 55, you should be able to see that this should reflect a diurnal variation. Right here, a diurnal variation of the total electron content. Yeah. The right plot here, I plotted the altitude density profile in log scale at 55 degrees and also for all the longitudes. So here you can see the contribution from the different layers to the total electron content. And this chart can also help you understand the NMF2 and the HMF2. So the NMF2 here, you can see, well, I need to adjust the color scale a little bit, but you can see the higher densities happens at higher altitude. Especially here, you can see it more clearly that the HMF2 should be actually somewhere around 300 something. It is interesting. Yeah, it's interesting to see that the chart here shows the HMF2 is below 300. So that's something that I don't understand. I hope we are looking at the same run.
It was for the very weak F10.7.
Oh, okay. So maybe we are looking at the different runs. I saw there are like at least a dozen of runs for the same day. Yeah, maybe I picked the run time. But you can use a similar way of generating the plots, and they will help you understand those curves. Yeah. So a general suggestion for looking at the simulation results is to make plots of those two-dimensional plots first, and then go to look at the line plots to take a look at the details, more quantitative values of those physical parameters. Yeah.
Thank you, Shasha. Two things. One, indeed, CTP does include a global dynamo. So so then the Appleton anomaly with a fountain effect should be in there. Am I interpreting that? Okay, great.
Yes, and that effect can be amplified beyond the terminator due to what we call the pre-reversal enhancement effect.
Great. Is this a good time to take a break?
Yeah, sure for me.
Okay, great. All right. Let's be back in 10 minutes.
Okay.
Okay.
See you later.
And
in the shared Google Doc. Yeah, so we can go through some of them, and some of the questions will be answered by the second part of the lecture. So, yeah.
So I'll leave that up to you as you can deal with them as you see fit. We can also save them for office hours.
Okay. Yeah. So the first question asks, when you look at or analyze some of the CTP runs, you saw two additional lines that at higher latitudes. So without seeing the plots, what I'm thinking is you are looking at the ionization of the Aurora zone. So you are likely seeing two extra like E regions in the northern and the southern hemisphere. So the Aurora ionization is another type of ionization that can cause the ionosphere E region. They are due to energetic charged particles coming from the magnetosphere. So instead of the solar radiation, which is the photons that's coming down and the photon ionization. So that's a different type of ionization process, but it's also very important for high latitude. So the polar cap absorption is due to more energetic ones. They usually happens when we have like solar energetic particles or cosmic rays, or in some cases, like we have very energetic one that's coming from the magnetosphere that can penetrate all the way to like 90 or even 80 kilometers and create that E region. So that will be the time where the high frequency radio communications can be absorbed. So we call them polar cap absorption. So depending on where this ionization that you saw, if it's driven by that, the typical conditions like the steady conditions that we just mentioned, you are not very likely to get a very energetic particle precipitation into the D region. So that's the first question. I hope I answer your question. So if you have further question following this one, please feel free to put in the chat. Then the next question is why the maximum value of NMF2 and TEC are observed around 8 UT instead of noon. I think this is the one that we looked at earlier. So, so take a look at the two-dimensional plot first, and then to select the specific location that you are interested in. Why do we see those finger structures? And this is also the equatorial regions we looked at before. So how much of the solar radiation can be filled and compressed to the point that it's harmful to human life on Earth? I'm not sure I fully understand this question, but I can answer partially. So a lot of the solar radiation, as you see, especially the short wavelengths ones, the X-rays to EUV, they will be absorbed by the thermosphere neutral components. And some of the leftovers, the UV band, will be absorbed further down in the stratosphere by ozone. This is why ozone layer is so important for our health. The most harmful UV bands, what we call the UVA, that's also the shorter ones comparing with the UVB and UVC. Those ones will be absorbed by the ozone layer. They can photodissociate the ozone, the O3, and make them become atomic O and then O2. So the good news is majority of those harmful UV lines will be absorbed before they reach the surface. And the bad news is we still need to do a very good job of protecting our ozone layers. Once they disappear, then the more harmful radiations will be able to penetrate down to the surface. So I hope my understanding of this question is correct. Then the next couple of questions will be related to what I'm going to talk about, and so I will defer them. So hopefully the answers will become clear after I give those slides. Okay, so now I'm going back to the lecture slides. Yeah, for some of you, if this is the first time to see some of the ionosphere chemical reactions, and don't worry, yeah, take your time, after the lectures to look at the slides and to digest them. So it will become more clear. So another thing that I just want to emphasize is the transition height between the atomic oxygen, that's the green line here, and the molecular nitrogen, since it's so important. Below roughly 170 kilometers, the N2 molecules are the dominant neutrals, and above that is the atomic oxygen. So from the chemical reaction slide, you learn about how important those two, the N2 and O, in terms of the photoionization, the source process, and also in the loss process, right? So the N2 is very important to destroy the O+ in the F region. So for us, we need to understand the relative abundance of O and N2. So that is why people created this one parameter called O over N2 ratio. Those chemical reactions actually give you the answer why we should care about O over N2 ratio. So in the F region, where the plasma density reached the peak, the production of the ionization depends on the atomic oxygen's number density, right? How many of those neutral oxygens there can be ionized? And then the loss process is determined by this first step, the charge exchange, and also controlled basically by the N2, the density, because the N2 density is order of magnitude larger than the O+. Remember, ionosphere is a weakly ionized environment, 0.1% ionization rate. So this first reaction is mainly controlled by the N2 density. So those chemical reactions tells us we should care about the relative change of the atomic oxygen and the molecular nitrogen. Okay, here is an odor simulation, but it's a very nice one illustrating how the ionosphere density profile would change once we shut down the source process. So here you can see that, at the beginning, we have a very nice, this is the F1 layer and the F2, the E region is somewhere here. Once we shut down the production, and so the density profile would be controlled mainly by the chemical loss process. So you can see within 1 hour, in the E region and the F1 region, the density almost disappeared completely. So this is 1 order of magnitude density change. And so we can consider that the E region completely disappeared. If you look at the finer time scale, you will see actually they disappear within seconds. For example, in the equatorial region, right after the terminator, the E region disappeared and only the F region will exist. So at a higher altitude, you can see the F region gradually decreases. It takes about 4 or 5 hours for the F region to decrease 1 order of magnitude. So this just gives you a quantitative impression of how different the E region and the F region's plasma lifetimes are. Okay, so there are a few questions in the shared Google Doc about the TEC asymmetries and the NMF2 asymmetries. So in order to understand those asymmetries, again, we need to understand the seasonal variation of the thermosphere composition. So what I'm showing you here is during a magnetically quiet, so that means there is no like solar storms or geomagnetic storms going on. It is just a typical boring day. I'm showing you that this is the left part here is the summer hemisphere, and the right part is the winter hemisphere. So in the summer hemisphere, you can think about this as during either December or the June solstice. So in the summer hemisphere, we get more solar heating, right? So the thermosphere can be heated more and have a higher temperature and a higher density. So a lot of those heating are absorbed in the E region and then the effluent region below the 200 kilometers, where we still have a rich N2, the molecular N2. So more heating in this region means that when the air extends to higher altitude, they carry what we call the molecular rich air into higher altitudes. So this molecular rich air expands to higher altitudes, and then they will move across the equator and then descend into the winter hemisphere. So this seasonal large-scale thermosphere circulation is driven by the asymmetric solar heating conditions in the summer and the winter hemisphere. Once you have those large-scale circulations that are going on, you are disturbing the O/N2 ratios globally. So in the summer hemisphere, you will see reduced O/N2 ratio because you have more N2 now here in the bottom. But in the winter hemisphere, you have more oxygen, that's descending into this region. So you will have an enhanced O/N2. If you look at the global average O/N2 ratio, you will see in the summer hemisphere, it's lower. That's shown by this blue curve. And it's higher in the winter hemisphere. So if you combine this with what we just discussed about the F2 layer density controlled by the O/N2 ratio, you will now start to understand how this large-scale thermosphere circulation controls the hemispheric ionosphere symmetry, right? So next, let's look at some real examples. This is the O/N2 ratio observation from the GUVI instrument on board of the timed satellite. So the satellite itself is, we only have the one of those, and they're orbiting around in the LEO orbit. So after a day, they were able to cover all the longitudes. So this is one example in January 18th, 2016. It was a magnetically very quiet day, okay? But here you can see that there is a very clear seasonal asymmetry of the O/N2 ratio, right? Higher O/N2 ratio in the northern hemisphere, which at this time is the winter hemisphere, and then lower O/N2 ratio in the southern hemisphere, right? So this observation directly confirmed this theoretical chart that you are seeing, this large-scale thermosphere circulation. Now, keep this in mind that we have higher, we have higher O/N2 ratio in the winter hemisphere, right? And now if we go back to the chemical reaction slide, we have more production, right? Like more O and then more production, and we have less N2, so we have less loss in the winter hemisphere. This is why the winter hemisphere can usually have a larger TEC and then larger NMF2. Okay. Let me go to that slide. Sorry for that. Yeah, so I directly jumped to this slide where I talk about the seasonal variation. So I showed you the theoretical chart of the thermospheric circulation, and also observationally, we can see those hemispheric symmetry, right? This is what the density actually really look like during those time periods. So the solid line here, why is it jumping around? Okay, so the solid curve here shows the summer condition, and then the dot lines or dash lines shows the winter condition. So look at the chart on the right first. That is the electron density. And here you can see the dash line, the winter condition, the density is actually higher than the summer hemisphere, right? So this confirms that, in the winter conditions, we have enhanced O/N2 ratio, and then we have more production than loss, and then that's why we have a higher density in the winter hemisphere. This was called the Winter Anomaly. Again, it is a seasonal variability, and so it's not really an anomaly. But I guess at the beginning, when people discovered this, they were surprised. They thought, we should have more density in the summer hemisphere because we have more stronger or more direct solar radiation. So here you can see, this is another example of how important the thermosphere is in order to control the ionosphere. Okay, so this is just one example showing you there is a density asymmetry. And similarly, the TEC will show you a very clear hemispheric asymmetry with larger TEC in the winter hemisphere. Okay. That's about the seasonal variation. The next, I want to briefly talk about the plasma thermal structure. We know the thermosphere temperature becomes isothermal above roughly 200 kilometers. And what about those plasma temperatures, right? So we can look at the electron temperature first. On the day side, the electron temperature has a local temperature peak around about 200 kilometers. And this local peak is due to related to the photoionization process. When the photons ionize the neutrals there, some of the remnant energy will go to those photoelectrons, and the photoelectrons will very quickly interact with the ambient thermal electrons and to give those shares the leftover energy into those ambient electrons. So that's why on the day side, we see a very clear local peak in those regions, indicated direct in the heat source. That heat source disappear on the night side. So the chart here on the right shows you there is a disappearance of that temperature peak in that 200 kilometer range, right? At the higher altitudes, you see the temperature becomes higher and higher, right? One of those reasons is because we have additional heat flux that's coming from the magnetosphere. The heat flux that can be generated in the inner magnetosphere region, like in the ring current region, and then due to thermal conduction, the additional heat will come down to the ionosphere height and then increase the temperature there. So that's why we typically see the temperature becomes larger and larger while you move to higher altitudes. The ion temperature is almost always sandwiched between the neutral temperature and the electron temperature. At lower altitude, the ionosphere temperature usually is usually the same as the neutrals because of very frequent collision between ions and the neutral particles there. So they share the same energy. If the ionosphere want to increase their temperature, the ambient neutrals will remove those heat very quickly. And we have a lot more neutral particles in the surrounding region, right? So it is hard to heat the neutrals. So at lower altitude, the ions and the neutrals usually share the same temperature. At higher altitudes, due to increased Coulomb collision or increased importance of the Coulomb collision between the ions and the electrons, the ion temperature will now become more and more towards the electron temperature. So due to those two different sources, this is ion neutral collision, and at higher altitude, Coulomb collision between electron and ions. So it determines the ion temperature. Okay, so the ion temperature, you don't see too big of a diurnal variation, but you do see that from the electrons. Now here is another chart from the Millstone incoherent scatter radar observation. Incoherent scatter radar is one of the most important tools for us to study the ionosphere. It can measure multiple physical parameters, the densities, the plasma temperatures, and also the plasma drift speed. What's shown here is the density, the contours, and also the electron and the ion temperatures. So as we mentioned before, we should see peak densities happening on the day side, right? And Millstone Hill is about, it's a sub-Aurora station. So I forgot the exact magnetic latitude, but somewhere between 40 and 50. So here you can see that during the day, we see the peak densities, and then the densities gradually decreases, reach the minimum just pre-dawn. Okay. As for the temperatures, there is a very rapid temperature increase once the station rotates to the day side. This is due to the solar heating. And then after that, the densities disappear, right? Once the density starts to disappear, we actually usually see some enhancement in the temperature, and that could be due to the heat flux coming from the rain current region. And Millstone Hill maps to a very good region where the rain current can exist in the inner magnetosphere region. Similarly, for the ion temperatures, you see a clear diurnal variation. Usually the temperature is lower than the electrons and follows the electron trend. So this is a diurnal variation. We already looked at the seasonal variation in terms of the densities. So here I want to highlight a very interesting feature of the temperature. So for the winter hemisphere, we have already seen, and due to the thermosphere composition change, we can have larger electron density in the winter hemisphere. If we absorb the same solar radiation energy, what that means is the larger the density, then the lower the electron's temperature should be, because now there are more of those electrons there to share the same amount of energy, right? So there is an anti-correlation between the electron number density and also the temperature. So you see there is a very clear anti-correlation between those two. The ion temperature is very weakly affected by those effects. Okay, so the last cycle here I want to show is the solar cycle variation. The solar cycle variation gives the largest variations in the density and the temperature. So if we look at the number density first, this is in log scale. The solar max, the density could be an order of magnitude than the solar mean. And this is simply due to that we have a lot more solar EUV flux during solar maximum. Again, the temperature of the electrons is inversely proportional to the density. So during max, we have more density, but then their temperatures are actually lower here. So this is another clear example of this anti-correlation between electron number density and their temperature. Okay, so now I'm planning to go to the second part of the slides while I'm translating here. Is there any question?
I don't see any questions in chat. Anybody want to speak up?
Your lecture is very clear, Shasha. Really enjoying it. Thank you.
Oh, that's great. Thank you, Amitava.
And you've got about 20 minutes left or so.
I know.
Great, no problem.
Okay, so I think what I just showed can explain some of those questions here, like what causes the variation of the TEC in latitude to be asymmetry, right? So if the question is about, you know, like a seasonal, the hemispheric asymmetry, I think what I just mentioned to you would explain that, right? The thermospheric composition change gives you the ionosphere hemispheric asymmetry and seasonal variation. The second question is, we can observe the close to the equator on night side. The TEC is always higher than the nighttime at higher latitudes. What's the reason for that? Close to the equator, TEC is higher than the night side at higher latitude. Oh, okay. This is the equatorial ionization anomaly that we just seen. Yeah. And okay, those questions perfectly direct me to the second part of the lecture, where we start to look at the dynamics. Okay, so in the earlier lecture, I was trying to give you some very fundamental basics about the ionosphere and thermosphere. And in this lecture, I want to talk about some more fun part, like the dynamics that's happening in this regime. Okay, so if we only have the solar EUV radiation, this is the ionosphere and thermosphere dynamics you will see. So most of them happen in the equatorial and the low latitude region. For the neutrals, they are mainly driven by the solar heating, and for the plasmas, and they are affected by those solar-driven neutrals, right? That will produce a fountain effect, and this fountain effect will be the one that's used to explain what we call the EIAs, or equatorial ionization anomaly. In order to understand that, we need to understand the E region dynamo. Okay, so this is a simulation result. It shows you the height integrated velocity in the, I think this is the height integrated velocity here in this panel. And this panel shows the height integrated currents. All of them are global maps, okay? And then this one is the Peterson current. I'm sorry, the C here is the Hall currents, and this one is the Peterson currents. Those two currents exist between 100 and 200 kilometers in the ionosphere. And those currents here in the on the day side are mainly driven by the solar heating dynamo process. When you have the neutrals that are driven by the solar heating, the neutrals tend to move from the high pressure or hotter area to the colder area, right? So once you start to have the neutrals to move, the neutrals will move the ions as well. And it is very important to understand the ion and the neutrals collide more frequently in the E region, but not between the neutrals and the electrons. The reason is the electrons can be considered as magnetized plasma, so they don't move across the magnetic field above 75 kilometers. So in many of those regions that we are considering, we consider that the electrons are bonded to the magnetic field. They don't move across the magnetic field, but the ions can. The ions collide frequently with the neutrals. So if we can have those neutrals that are, move around, they move the ions around. What that tells us is we might have a charge accumulation situation, right? So if we look at this B part, there are some divergence and convergence of those currents. And those currents here are carried by the ions. So that means in this case, on the dawn sector, we will see a convergence of ion currents. And so that means we collect more ions on this side. And similarly, there should be a deficit of those ions on the other side. So another way of thinking about this is that we accumulate positive charge particles in the dawn sector, and then negative charge particles in the dusk sector, right? Because the ions have been moved to the dawn sector due to those Peterson currents. This charge separation condition set up an electric field that's pointing from the dawn sector to the dusk side. You can see this is the electric field pointing here, right? And this happens in the E region. This electric field is eastward on the day side, and then westward on the night side. Once we understand there is a electric field produced by those charge accumulation, now we can understand the EIA formation or the fountain effect. Okay, so now the viewpoint is changed. Okay, the positive charge particles are now further out here and negative charge particles here. This is like we are looking at the the equatorial ionosphere region from the dawn sector and looking towards the dusk. Okay, that's the viewing geometry. And we see those magnetic fields, moving from the southern hemisphere and all the way to the northern hemisphere, right? So spend a couple of seconds and understand the geometry first. We are standing in the dawn sector, looking towards dusk. So this is the eastward electric field that we see here, right, on the day side. Okay. Because the Earth's magnetic field can be considered as equipotential. So once we generate the electric field in the E region, this electric field will map to the F region as well. So everywhere here in the F region, it will feel the same eastward electric field. Now we consider here, right at the equator, the plasmas in the equatorial region will move in what we call the E cross B drift direction. So if the electric field is pointing eastward, now raise your right hand here. Okay, the E cross B means your electric field in the eastward direction, and then the magnetic field now is pointing northward, right? So E cross B gives you a upward drift, right? So now the plasma here in the F region starts to drift upward to higher altitudes. Once the plasma move to higher altitudes, they will start to diffuse backward down due to the gravitational pulls, right? And the pressure gradient force. So you start to see there is a circulation, right? The equatorial plasma move to higher altitudes and then descend to higher latitudes, but lower altitudes. See this circulation here. So this is the formation mechanism of the equatorial ionization anomaly. We are accumulating plasmas in the off-equatorial region. Okay, so this is what also people call the fountain effect. And so there are a lot of text in the chat, and so let me see whether those are questions.
That's mostly me and Awatava
Okay.
going back and forth on the peanut galleries. So there aren't any student questions. You can ignore us.
Okay. Let me go back to one of the nice charts I showed earlier. So due to that equatorial fountain effect, the plasmas near the equator are now moved to higher latitudes, and then they descend to off-equatorial latitudes, and that builds those beautiful two ribbons. This is the EIAs. Okay. So the interesting thing is that those plasma dynamics are driven by actually the solar heating neutral wind, right? The neutral wind that's generated those dynamo electric fields driven by the solar heat in the E region. This is also the reason I'm asked earlier whether the CTP here turned on the dynamo process. Yeah. Okay. Next, because we have very limited time, but I do want to mention the high latitude process. The high latitude process in the ionosphere is a completely animal. So in the earlier chart, I showed you this one, right?
Hey,
we only consider.
Shasha?
Yes.
Before you go on, so there's a question from Nilam. What is the the equatorial electrojet?
Oh, what is the equatorial electrojet? That's a very good question. That is not covered here, but I can say it very quickly. So on the day side, near the equator, in the E region, there is an enhanced ionization area due to the solar radiation, right? And there is another effect called the Cowling effect. Some of you may have heard about that. That is an effect that could amplify the conductance in that region. So on the day side, directly facing the sun, we have a uniquely high E region conductivity, and that will be able to serve a large electrojet. So that is why we have this eastward electrojet on the day side. And we only have them on the day side because we need that E region very large conductivity effect. Okay, so let me come back to this chart. When I show this, I mentioned this is a chart where we only consider the solar EUV as the energy input for the IT system, right? In reality, besides the EUV, we also have the solar wind blowing from the sun to the earth. This is another type of energy source for the system. The solar wind will interact with the magnetosphere and then generate a lot of dynamics in the magnetosphere. The magnetosphere will then send the currents into the high latitude regions and starts to drive the convections in the high latitude region and create the Aurora zone. So all of those dynamics that's happening in the high latitude region is because we have the solar wind as the additional energy, and then the solar wind interact with the magnetosphere. So this is another plot just trying to show you the importance of those two energy sources. The solar radiation, directly photon can penetrate to low altitude. But if we want to consider solar wind, those are charged plasmas that's sending out from the sun. We need to consider how the solar wind interact with the Earth's magnetic fields, the bubble here, right? Very quickly, just show you a simulation. This is our Earth, this is our magnetosphere, and we have our solar wind that's coming down from the sun. You can see here there are some density fluctuations, and they interact with the magnetic field, generates a very dynamic magnetosphere. Okay.
Shasha, another question just came in. Do Raspy waves have any role to play in the ionosphere physics?
That's a very good question. Yeah. So there have been a lot of research and interest in recent years studying the interaction between the lower atmosphere dynamics and the ionosphere and the thermosphere. So Raspy waves, gravity waves, and planetary waves, those waves people are often talking about, their impact can penetrate to the ionosphere and thermosphere region. So the short answer is yes. I myself, do not do research in the lower atmosphere region, so I don't have a more in-depth answer to this question. But the short answer is yes. Okay. Yeah. So next, I want to just highlight some of the important processes that drive the high latitude ionosphere and thermosphere dynamics. In the previous slide, this one here, you see that once we add solar wind, we start to have those high latitude dynamics. And if the solar wind drives the magnetosphere real hard, for example, during a ICME or CIR storm, then both the high latitude system and the equatorial system will expand. So they start to interact with each other. And there are some very interesting features that you will see during storm time. So a very brief introduction of geomagnetic disturbances. Geomagnetic disturbances are driven by solar wind and the Earth's magnetic field interactions. And they can be either due to coronal mass ejection or co-rotating interaction region, right? So they generate the largest disturbances called a storm, or there can be some intermediate level disturbance called substorm. But be careful, the substorm is really not a small storm. It's a completely different phenomena. Or the shock compression when we have a very strong velocity, solar wind velocity increase or density enhancement, they tend to compress the Earth's magnetosphere and generate a shock compression. All of those impact will affect the ionosphere and the thermosphere. So due to the very limited time, I would like to jump directly to what we call the magnetosphere-ionosphere convection process. So here it shows you the side view of the Earth's magnetosphere. At this time, the Earth's magnetic field is pointing northward. The reason I'm saying this is we do have those magnetic polarity flips, right? So now the magnetic field is pointing upward. If the magnetic field that's carried by the solar wind that's flowing into the nearest region has a southward component, we will have a process called magnetic reconnection happening right here, where the two magnetic fields are opposite to each other. So the magnetic reconnection happening in the day-side magnetosphere will also affect the ionosphere high latitude convection. They open the field lines, and then the solar wind will carry the open field line to the night side, where those magnetic fields can meet again and reconnect. This is what we call the night side reconnection. After the night side reconnection, the newly generated closed field line will drift towards the Earth and eventually return back to the day side. So finish a complete circulation. The complete circulation is facilitated by day-side and night-side reconnection. The same process drives the ionosphere convection. And this is what we call the two-cell convection pattern. You know, if any of you as do research for the high latitude ionosphere and thermosphere, this will be one of the most important plasma circulations that you will learn. Okay. So we are really having very limited time. So I'm gonna jump directly to some of the interesting parts, if that's okay. Yeah, I prepared a lot of slides. Okay, let me jump to this one here. Now, you understand that the magnetic reconnection can drive high latitude ionosphere convection, right? And I also mentioned to you, there are a lot of neutrals in the surrounding region. So once the ion starts to move, they feel the neutrals. If the magnetosphere drives the ionosphere really hard, the ions can actually drive the neutrals. So that creates the neutral circulations in the high latitude region. And very interestingly, is the neutral circulation tend to mimic what the ionosphere convection is. So for example, this part shows during a northward IMF condition. This is the plasma drifts. You know, it's kind of chaotic, but you still can see the pattern. This is what the neutral wind looks like. You see, it's like a simplified version of this ion drifts, right? The magnitudes are smaller, but in terms of the direction of the drifts, they follow each other. So when we drive the high latitude ionosphere strongly, the high latitude ionosphere transfers the momentum and energy to the neutrals and starts to drive the neutral wind, makes them to mimic the ionosphere convection. So this is one way of understanding the magnetosphere, ionosphere, and thermosphere in 2 minutes. The other interesting part is, you know, the solar wind is highly dynamic. That means we can have reconnection-driven convection, and they can be shut down in a second, right? So, but in the high latitude region, you know, once we start to drive the neutrals themselves do not directly feel the shutdown of the reconnection. Once they started to drift in the same direction as the ion convection, even if we shut down the ion drift, the neutral still moves. And now it's the neutral's turn to drive the ions with them. So the ions now will have almost the same convection pattern, you know, following the neutrals, and which mimic what the previous time history of the convection is. So this is a very interesting ionosphere and thermosphere feedback in the high latitude region. Okay, so we are running out of time. I will stop here and answer questions. We just get a 10 minutes tour of the high latitude IT dynamics.
Shasha, thank you so much, and certainly everything you covered was valuable, and of course there's always more to learn. So we've got a couple of, well, there are a couple of questions in chat. One's about a substorm, which the definition of a substorm, which may be better to punt on. I'm not sure if you feel like you're qualified to
Yeah. I did my PhD on substorm.
Oh, never mind.
Yeah. So I'm very happy to answer this question.
So I think there's this perennial question: is how does a substorm related to a geomagnetic storm, and are they related? And
okay, yeah.
And
so
I've never figured this out.
The relationship between substorm and storm is very complicated. As you can see from the name, in the earlier days when substorms were discovered, right? They thought they were just the smaller scale storms, but then later people figure out they are actually respond due to very different dynamics, but still they are related. Okay, so the definition of substorm is usually based on an index called Aurora Electrojet Index. You will see people use AL or AE index to represent this. This is an electrojet that's happening in the Aurora zone, 65 to 70 degrees latitude. And so when we have a substorm, this electrojet will increase significantly. And so we use this to identify substorm. Of course, there are other mechanisms of identify substorm. The best one, or I have to say my favorite, is to directly use the Aurora observations. So during a substorm, you will see a sudden brightening of the Aurora within the Aurora oval, and then it very quickly expands in all directions. So within 10 minutes, it could cover several hundred kilometers times several hundred kilometer area, a big area on the night side. So with that said, substorm usually refers to a smaller scale dynamics that's happening on the night side Aurora zone. If you map that into the magnetosphere region, that is usually related with what we call a nearest magnetic reconnection region. And the if you map the substorm onset to the tail, you will see the location is typically around 10 to 20 Earth radii. Okay. For geomagnetic storms, the definitions are based on the DST index, traditionally DST, or you can use a higher time resolution, what we call the symmetric ring current index. That's a 1 minute one. So this index measures the strength of the ring current. The ring current occurs at a much closer L shell. Here I'm just used one of the simulation results to show you. This is a ring current region, within like 10 Earth radii. And during a storm, you will see an intensification of this current here and here. And so this is the current that's floating westward. So westward current will give you negative perturbations on the surface. And that's why we see negative perturbation in the DST index. So the short answer of the relationship between substorm and storms are, they are different and they are reflected or measured by different indices. One is Aurora electrojet and another one is the DST, which measures the ring current intensity. So that's really a short answer for the substorm-storm relationship. Yeah. And I can see the next question is, can we expect a reconnection process at night similar to the day side? I mean reconnection due to southward IMF and northward Earth mag field. So on the night side, the reconnection are usually due to the Earth's own open field lines. So if I'm showing you this slide again, so you can see this curve where the field is pointing towards the Earth. And then this one in the southern hemisphere is pointing away, right? So if those two fields move closer to each other, they can reconnect again. And this is what the night side reconnection configuration usually look like. Oh, there are a lot of comments that's talking about substorm and storms. So it's great. So I saw a lot of the comments are actually like people are trying to answer the questions there in the chat as well. So I don't see a distinct or a new question that's coming out from that. So Nick, maybe we can directly jump to the office hour. Is
Yeah,
that
I
okay?
think so. Yes. So we'll. So if we've got office hours and you want to talk to Shasha more about her lecture and ask follow up on any of the questions, I think that some of the questions were might involve some follow up. That would be great. Otherwise, we can go on a break. I have a couple of things for you to do during break. I'm gonna on the mural board as a way to get you to read through the various. Well, I like to get your some opinions on the various topics that are up there. I'm gonna open up. There's a possibility of upvoting, so I'm gonna open up a voting session. And I'm going to give everybody 5 votes. So you can upvote. Who can name? Yeah. So over the course of the break, you can read over the mural board and upvote any of the comments that are there, and provide. And you get 5 votes. So you can upvote 5 comments that are there. So and I'll talk more about how I want you to think about these when we begin the next session. And then also, well, I'll talk about that at the end. We've got a survey going out to you, a post-workshop survey going out to you, but I'll talk about that at the end. But, new game every time Nick says, take a shot. Yeah, okay, thank you.
Sasha, if you don't mind, since the students aren't asking, you didn't get the time to dwell on this, but you mentioned the GITM model in one of your slides that we didn't get a chance to cover. Could you give us a sense in terms of global modeling, where some of the gaps are in terms of getting the ionosphere, thermosphere in global models?
Mm-hmm. Yeah, I would be very happy to answer that question. So I personally, because I'm here in University of Michigan, right? So I'm part of the SWMF team. And so I'm using a lot of the global ionosphere and thermosphere model or the GITM model. In my mind, some of the challenges that we are facing of those global models, we actually do not have a very good description of the drivers. So in the last 10 minutes, I showed you how important the solar wind magnetosphere interactions is for the high latitude ionosphere and thermosphere, right? And that heating or that energy input is highly dynamic, much more difficult to simulate than the solar radiation impact. So if we want to understand the ionosphere and thermosphere better, we need to improve the specification of the high latitude drivers and include the ionosphere convection and also include the Poynting flux or the Aurora energy that's coming down to that region. So I personally would be very interested to see, what are the different ways that people can use to to improve those energy specification. For my work, I have been using the BASRS coupled with RCM. That actually is doing a pretty good job in terms of describing the convection patterns. And but then the conductivity is still a challenge, as you see probably for a lot of the other models as well.
Mm-hmm. So the RCM model, a next generation RCM model, which has been so successful, but also quite legacy in many ways, would be an important area of work.
The RCM and also the here's a CME or CRCM model that we used before. That's another way of describing the inner magnetosphere region. Those inner magnetosphere models are very important to capture the ring current dynamics. So it's an absolute must to be coupled to the global magnetosphere to successfully simulate the magnetospheric dynamics.
Yeah, and given what you said about the importance of the high Z ions, the outflow problem, and so on and so forth, it would be important to get more species into this, right? Now, RCM has a lot of species already that it tackles, and it tackles quite well. But the coupling between RCM and the global models is probably not as good as it can be. We can probably do better in that area, would you say?
Yeah, absolutely. I think most of the time we are just taking the pressure, right, coming from the RCM model. And I don't think that there is or maybe there are, but I don't know, the self-consistent way of describing the heavy ion existence in the magnetosphere. We have the multi-fluid, multi-species MHD models. I'm not familiar how that is, calculated in RCM. Yeah.
Thank you. That's very helpful. Thank you.
So there is one more
and
question
I
in the
saw
chat.
Neelam had her hand up.
Just now the Amitava was talking about the outflow. So I just want to know about what is the outflow, the ionospheric outflow, and what is reason for that, please.
Okay. Yeah, so the ionosphere outflow usually refers to the ionosphere or those plasmas that are generated from the ionosphere, and then they move along the polar magnetic fields and then contribute to the plasma content in the magnetosphere. People are very interested in O+ outflow, and the reason is that the O+ outflow may have a significant impact on the reconnection process of the magnetosphere. They could mass load the magnetosphere and change the reconnection rate and the reconnection location. And you start to see that there should be a feedback mechanism there, right? Once you change the reconnection location, then you change the global dynamics. So that's why people are very interested to know about O+ outflow. The difficulty of simulating O+ outflow, there are actually several factors I think that are very important that people need to get it right. The first thing is about the actually lower altitude ionosphere thermosphere coupling. Because I mentioned all of those chemical reactions, so you can see that the O+ density is controlled by the thermosphere as well, right? So that means we need to self-consistently deal with the ionosphere, thermosphere, and that will give us a better idea of how much of those O+ flux are actually available to flow out. And then the next important and very challenging thing is about the acceleration of O+ particles. We have very limited observations above 1,000 kilometers to like the Aurora acceleration altitude, so like to 1 or 2 Earth radii. Within this region, the O+ usually changes there or get energized from what we call the ion upflow to ion outflow. They really gain the energy within that region to become, to be able to escape the gravitational pull and then reach the magnetosphere. So those are the two most significant challenges that I see for ion outflows.
Thank you.
And there's a couple of questions in chat. Mahith has a question, and then I don't know if Dinesh wants to clarify what he is asking about. But I want to go with Mahith first, if he's there.
Sure. It's more related to the question of irregularities in the ionosphere. So I just saw like a couple of slides where there were like some mentions of the ionospheric irregularities. I just like wondering whether these plasma irregularities are usually composed of just electrons or ions, or whether they are combination of them. The other question is that I know that they are field aligned, like the magnetic field of the Earth just elongates them along their direction. I just wondering like the reason for that. So if you would be able to give some comments on that, that'd be grateful.
Yeah, there are a lot of plasma irregularities in the ionosphere, and some of the most famous ones are like near the equator, you get the what we call the equatorial plasma bubbles, right? And in the bubbles, there are a lot of irregularity. And in the higher latitude regions, we also get those irregularities associated with large density gradients, like polar cap patches or plasma density holes. So a lot of those irregularities happen in the F region or in the topside ionosphere. So the F region and topside ionosphere, you started to see the neutral density decreases very rapidly there. And so the ions and the electrons are usually considered to move together with each other, follow the E cross B drift. So that means that when you see those irregularities, you can consider charge neutrality, right? The ions and the electrons move together. Yeah.
Okay, perfect. And like any reason why these plasma gets elongated along the field direction? Like what force is really acting there?
You mean why they are getting field aligned?
Yeah, like the reason why plasma is getting elongated along the field direction.
Yeah, so in the F region where the collision frequency becomes smaller, so then their gyro frequencies become more important. So you can now consider ions and electrons both magnetized. So once they are magnetized, they tie to the magnetic fields. It's much easier for them to move along the magnetic field rather than move across the fields. So that's why a lot of the structures are, field aligned. And near the equatorial region, take the bubble as an example, right? When we study the equatorial plasma bubbles, we usually consider flux tube integrated quantities. And I mean, that's another way of describing the plasma dynamics there is that, the Earth's magnetic field near the equator is like an arch, right? So if you want really Taylor exchange the flux tube, you have to consider the flux tube integrated quantity. And I don't know whether this exact answers your question, but I think the earlier comment about, the reduce of the collision frequency and both ions and electrons are magnetized, that is better, I think, or easier to understand when you consider the field aligned structures.
Maybe I can help just a little bit more. If you're thinking of a fluid picture, the classic instability in the F region is the gradient drift instability. And the gradient drift instability is like a Rayleigh-Taylor instability, if you like, because it's really, as you said, it's like the E cross B flows that are really important. And so if you go by the intuition on Rayleigh-Taylor, then these tend to align themselves in such a way that they have the property that K dot B is equal to 0 or as close to 0 as possible. So you see that feature actually show up in these studies as well, numerical studies of gradient drift instability. And then if you go down to really small scales, you have the Farley-Buneman instability and things like that, which worked on by people like Mears-Oppenheim, which are very short wavelength instabilities that are also present. But the proper way to describe them would be through particle and cell codes. Whereas the F region a gradient drift, you can actually use fluid equations for. And it's a very active area of work, by the way, and some of the most beautiful results, plasma turbulence was done with F-region instabilities. I hope that helps a little if you're looking for a fluid picture. I do not disagree with anything that Shasha said. I was just adding a few more comments if that helps.
Yeah, those are very good
perfect,
comments. Yeah, the gradient and drifting instability is very important for the polar regions to form those plasma irregularities that's causing the scintillations in the high latitude region.
Perfect. Thank you.
Neelam, did you have something related to what was just discussed?
Oh, hello.
Yeah. Was so I wanted to get Dinesh's question in, but was your question related to what was just discussed, or?
No, the new question I have.
Okay, let me get Dinesh in first, just because he's got so misunderstand. So Dinesh, you want to? I can't follow the chat thread. You want to clarify anything?
Okay, sorry. I just saw the famous depiction of the IMF and the Earth's magnetosphere interaction, where I just usually see the day side Earth's magnetic field is interacting with the IMF north or south, but I see the reconnection process in the night side in a different way. That is through the open south and north magnetic field of the Earth only, but not with the IMF. I was just maybe misunderstanding the 2D picture of the magnetosphere, maybe. So am I wrong or right? I don't know. Please just let me know why we don't show the IMF interaction, locally in the night side of the Earth magnetic field, magnetosphere. So
yeah, that's a very good question. Yeah, the reason is because the geometry is a little different. So on the day side, the Earth's magnetosphere is compressed by the solar wind, right? And on the night side, it was elongated. So if you think about the geometry, it would be much harder on the night side for the southward IMF to reconnect with the Earth's magnetic field. Yeah, but those reconnection process can occur off the subsolar point. They can also occur on the flank side when the conditions are right. Yeah.
Okay, great. Thank you.
Neelam.
Yeah, I want to know about the STEAM, that is a strong thermal emission velocity enhancement, which is the Aurora, but not Aurora. So what do you think about that, and what is the mechanism for that?
Yeah, that's a very good question. So Steve is a very interesting phenomenon. I still remember that a couple of years ago during the AGO meeting, when Steve was first presented, and then we were Eric Donovan from University of Calgary, is one of those co-authors on some of the earlier papers, and he just called it Steve because when the citizen scientists discovered Steve, they previously thought it was an Aurora arc, and then and the Aurora arc, because that happens in the subaurora zone, so it must be due to other than the electrons, like the proton precipitation. But Eric said it couldn't be due to proton precipitation because it's just too narrow and too structured. And so before we know what it is, let's just call it Steve. So this is why the Steve got its name, or how it got its name. It's very interesting. And then during that AGO session, Bob Lysak from University of Minnesota just made up that full name for Steve during the session. Let's just call it strong thermal emission due to velocity enhancement, something like that. Yeah. And Steve carried his name. And so it's a very interesting story about the discovery. And then later, in the last couple of years, there have been a lot of working on Steve, and people have been trying to identify, when we see Steve optically, what are other companion plasma dynamics or properties on. So people have used the LEO satellites like SWARM. So SWARM can cross Steve, and then they can measure the plasma drift, they can measure the temperature. And so what they found is the plasma speed within Steve can be as fast as 2 kilometers per second or even higher. So that is a very narrow region with very large plasma speed in the ionosphere. And the temperature is also very high. So we know this is a region with very large frictional heating, right? And with very large plasma flow speed. So on the other hand, people have been using the different ways to measure the spectrum of the Steve optical emission. And what I remember is that they think a lot of the emission is actually coming from the NO continuum instead of a more discrete like aurora emission we usually observe, like red aurora, that's 630 nanometer, or green aurora, 575 nanometer. And this one is a continuum, not a discrete one. So I think the key is in understanding the ion neutral couplings in that region and understanding the enhanced neutral species and their optical emissions.
Yeah. Okay. Thank you very much.
Mm-hmm.
And Luke has his hand up.
Thank you for the very nice talk. I just wish we could have listened to all of your slides, but so I have a very small question, like that you said during higher amount of solar radiance, the variation in O by N2 ratio changes the density of changes the variation in electron density. So like in the summer hemisphere, because of the rich nitrogen pulled up in the gets pulled up in the upper atmosphere, and it helps in reconnection. So I was asking that at the same time we also get lots of solar radiance in the same hemisphere, which also helps in production rate of ions. So how do we decide that which parameter of these two are more prominent?
Mm-hmm. Yeah. So yeah, there is a lot of noise on your side. So I think your question is about the seasonal variation of the ionosphere density, right? So in the summer hemisphere, we get more solar radiation, but on the other hand, we also have reduced the O over N2 ratio. So there is a competing impact. You increase the source, but then you also changed the atmosphere to be ionized. And which one is more important, right? Is that your question?
Yes.
Mm-hmm. Yeah, that's a very good question. Yeah, indeed. In the summer hemisphere, you get more solar heatings, but then the O over N2 ratio change is demonstrated to be larger. The impact is larger than the solar radiation change itself. Yeah. A better way of understanding that would be a term analysis. Use the global ionosphere thermosphere simulation to calculate more quantitatively their impact. Yeah.
Thank you.
Mm-hmm.
All right. Are there any other questions for Shasha, or comments, or? Okay, great. Shasha, thank you so much.
Mm-hmm.
I really appreciated the talk. I learned a lot, and so even though you couldn't get through everything, there's a lot to get through for the ionosphere. So
yeah.
Somebody was commenting on the processes diagram that you had at the beginning of your second talk, and that's there's a lot going on.
Yeah, exactly. And that is one of my favorite picture for describing the IT dynamics. It's really a very dynamic regime and very interesting. So another thing I want to mention is that, I prepare a lot of slides, but we have limited time. But if you are interested to know more about how the ionosphere and thermosphere responds to geomagnetic storm, I gave a CEDAR tutorial last year, and I believe that tutorial is still available online. And so you can go and find that from the YouTube site or from the CEDAR workshop site. So you will be here, be able to hear the IT dynamics during storm time.
Great.
Shasha,
Feel
can
free
I
to-
also just clarify, do you want me to post your slides as is that you uploaded?
I will make some modifications just based on what we discussed. Yeah,
Very good.
and I
Okay.
will upload the latest version this afternoon.
Excellent, thank you.
Great. Thanks, Shasha. Why don't we, I know it's 11:20 right now, or what, 1:20 or whatever. It's 20 after the hour. Why don't we take a 5-minute break for those who couldn't step away, just to make sure, just to take care of everything, and we'll come back at 25 after the hour and go into the brainstorming session that and try and take advantage of Lika's availability as much as we can.